Good stuff. Right, good morning, everyone. We will just give it a couple of minutes for everyone to join. While you're waiting, we are going to be using Mentimeter this webinar. So I think a lot of you probably will have used Mentimeter before, but if not, it's menti.com. I think Drishti will put a link for us in the chat, and then you just need to enter the code on this screen, or you can scan the QR code alternatively. You don't need to do anything while you're there. We will get to questions as we go through the presentation. So you just need to have the screen open and ready for later in the presentation. I'm just going to hop back to the title slide, but we will put the code in the chat for you. For those of you that have just joined, we're going to be using Mentimeter for this presentation. So the link is in the chat. The code is also in the chat. So if you just go to Mentimeter, type in the code, and then just have that screen open, and we'll use that during the rest of the webinar. Okay, I think we'll get going then. So welcome everyone to the first part of a new series that we're doing as part of the Road Safety GB Analyst Network webinars. And I think this is our first webinar since July. So we've had a bit of a break over the summer and back with a bang with statistics. So we're kicking off a new series on statistical approaches to collision data, this one being part 1. And in this one, we're going to be looking at some principles and pitfalls. So it's going to be quite introductory, quite discursive between me and Drishti, and hopefully fairly informal. We'll get you involved in Mentimeter and in the chat as well to discuss some kind of key things to be aware of when we're doing collision data analysis based on our experience. So as I've said, we're going to be using Mentimeter for this webinar. The link is in the chat and the code is in the chat as well. So when you get a moment, do log into Mentimeter and put the code in. Right. Okay, so what are we going to cover today? So we'll look a little bit at some statistical basics. So we'll cover some uses of statistics and some jargon as well, and maybe what some of that jargon really means. Hopefully we'll break down some common pitfalls in statistical analysis of collision data, particularly pitfalls that relate to our field and challenges that we might have with collision data and how we need to be aware of those. And then if we have time, and this is a big if, because when Drishti and I were putting this together, there's a lot of stuff we thought we could say as a bit of an intro. So this is at the end. If we have time, we'll talk a bit about when you might need to consider a stats test or a stats model as a bit of a kind of preamble before future webinars in this series that will dig into some of that in a bit more detail. So we'll kick off then with some statistical basics. So what is statistics? When we say statistics, what do we really mean? So this is a Wikipedia definition of statistics. Yeah, the code should be in the chat, Amanda, and then there's a link there. So hopefully that works for you. So yeah, this is a Wikipedia definition of statistics. It's the discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. So basically anyone that does anything with data, according to that definition. This is an Oxford University definition. Okay, Drishti, can you reshare the
yeah, I'll do that.
Reshare the code, please. Thank you. Sorry about that, guys. We will have a screen that has the code on it later as well, so you can do it then too. So Oxford University, this I've taken from the statistics undergraduate admissions page. it concerns the theory relating the characteristics of a population to the statistics drawn from some sample of its members. Basically, in other words, what can we learn about all drivers by studying some drivers, or what can we learn about all people by studying some people? So according to these definitions, you could say, are we all statisticians? We're at least all statistics adjacent, I think. I think everyone in this room would probably agree with that. No time to discuss it, unfortunately, but certainly we all have some kind of involvement with statistics in our roles. And where does statistics fit in with the kind of broader spectrum of artificial intelligence, machine learning, a lot of these kind of buzzwords as such in today's realm of analytical techniques? So statistics fits here. This is taken from a cardiology journal that I found. I think this is one of the best depictions of this kind of realm of analytical techniques that I've managed to find. So there's a bit of overlap between stats and AI and machine learning, particularly as you move into the statistical model side that will ingest data and then maybe make predictions based on that model that's been created from the data. We'll talk a bit about descriptive statistics and inferential statistics. We're not going to cover AI and machine learning in this webinar. Indeed, that would be far too much material to be covering. But there's a whole world of other things out there that are kind of expand on a lot of the groundwork that maths and stats has done over the years. And recently we've seen, as I'm sure all of you are aware, significant advancements in some of these other techniques in here. But statistics fits in kind of on the left-hand side of this diagram. So we're going to get some Mentimeter stuff going. Hopefully you've all managed to get the code in and see the screen. And I'm going to hand over to Drishti for this section.
Yep.
So this is the code and the link.
I can already see 52 people on the Mentimeter thing, so I think that it's gone through. So already some responses coming in for this. So when do we hear the word statistics? What comes to mind? So statistics can mean many things to many people, and it'd be really interesting to get some words in regarding to that. So I can already see some responses coming in for that, and we'll give a couple of minutes before we deep dive into this. So the common consensus is that it's about data and numbers. There's also some people that have put in complexity, uncertainty that comes with that. That's also quite interesting. It can be really complicated. Yeah, it's filled with jargon.
Yeah, it's interesting reading some of these. Some people seem to be a bit down on statistics or unsure about statistics from these comments. Other people seem to be using it in lots of different purposes.
Some people have also brought in the data visualization, the manipulation, analysis side of thing, and how it can show reliability and trends in the data.
Yeah, cool. So a lot of you, I'm guessing from this, fairly comfortable with using stats in one purpose or another. Some of you less comfortable with using stats. A lot of reference to kind of numbers, calculations, data, graphs, quite common uses of stats that I think we're all probably involved in. Okay, should we move on to the next one?
Yep. So we've covered what does statistics mean to us, but what do we use statistics for in our individual roles? It'd be good to get some responses coming in for that. And hopefully the slide has changed on your Mentimeter as well. Okay, I can see some thumbs up coming in.
Yeah, not too many surprises, I think, in what I'm seeing here. Interesting, the first one to come up was collision modeling. That's been drowned out a little bit by analysis.
A lot of focus is on data-led evidence and the analysis part of it. Yeah.
Yeah, and I've lots of things here that we'll chat about later, actually. Trends, inference, evident, counterfactuals, informing. Look, I imagine in this room, or in this virtual room, we have quite a few analysts, maybe some policymakers that are stats adjacent, and that's definitely coming through in this, in terms of some of you focusing on the analytical technique that you're using, others of you focusing on what it can do for you in terms of the evidence or the policy making and that kind of thing. Move on then.
So drilling this down a bit more into what kind of statistics do you use in a role? So it can be descriptive statistics, so describing the data through figures, percentages, statistical testing in terms of Wilcoxon test, chi-square test, t-test, or statistical modeling in terms of linear regression, Poisson regression, budget regressions, and of course there's also machine learning.
Yeah, and note you can select multiple options for this one. So I imagine some of you might be using all of these. Others of you maybe just one of them, or none at all.
I can see the descriptive statistics pulling in, with the majority of us focusing on descriptive statistics and a bit of us focusing on stats testing.
Yeah, I think this is about what I expected.
Yeah.
I'm somewhat relieved looking at this that you've not all said machine learning, and that we're maybe pitching this at a different level. Yeah, the most of you are involved in stats, in kind of presenting figures and percentages and that kind of thing. Some of you have moved into stats testing, even stats modeling. A few of you have used machine learning, which, as I said before, we're not going to unfortunately cover that in this session, but certainly a lot of the principles are still relevant. So yeah, in this one, we're going to talk about mainly descriptive stats and then the principles surrounding stats testing and stats modeling, and some of the key things that we just ought to be aware of in interpretation and that kind of thing.
Well, so I think we can move on to the next slide.
Great, that's useful context.
So drilling down a bit more into the descriptive versus inferential statistics. So descriptive statistics, as the name suggests, it's all about describing and exploring what your data is telling you, be it through data visualizations like scatter plots, box plots, or equally, it could also be through percentages, rates, or ratios. So for example, on this slide, we're looking at, on average, the collision rates have dropped by 50% in Area 1 after implementing an intervention. So that'll be more about describing what the data is. And if we go to inferential statistics, it's more about inferring what the data means, actually understanding whether there's causation, whether there's a statistically significant difference between your two groups or the hypothesis that you have. We can equally also make predictions, so forecasting as to what would the collisions be. And also testing and hypothesis. So for example, if we implement speed cameras, we can say through statistical testing that there's going to be a statistically significant difference or reduction in collisions in Area 1. And both of these are really interdependent on each other. So you might find a trend in your data through some of your visualizations that you do and be like, oh, hold on a minute. I want to really understand whether there's causation in my data or whether there's a statistically significant difference. And then you might go on and do some collision modeling, some statistical testing. But equally, you might do some statistical testing and see that, oh, hold on, this is not the hypothesis that I had. And you might go back to descriptive statistics and actually see that what is the trend in the data and why am I seeing what am I seeing? Sort of the thing. If you click ahead, Nathan.
Yeah, great. Yeah, I was just going to comment on this slide, actually. I think that interdependence is really important. I usually find when I'm doing analysis that I rarely do inferential statistics without doing descriptive statistics first, because it's the descriptive statistics that gives me a sense of what's going on in the data, what I need to think about, where I might be seeing some changes or some relationships, and then the inferential statistics somewhat kind of confirms that. I'm interested to know what other people think on that one. Yeah, and here's some examples of what might fall into inferential statistics. Do you want to comment on those at all, Drishti?
Yeah, just that inferential statistics is really interesting. So we can obviously have the basic stats testing side of it, be parametric, non-parametric stats testing. We're just comparing two groups and understanding whether there's a difference between them. So using t-test, chi-square test, and then of course there's a stats modeling side of it with linear regressions, logistic regressions, Poisson regressions, when we're interested in seeing the relationship between multiple variables with your variable of interest. So yeah.
Great. At the start, I realised I should have introduced ourselves for those of you that don't know. It's never too late for an introduction. So we're both in the consultancy team at Agilysis. I imagine most of you will know us or have seen us before, but we both take a role in the more quantitative analytical side of things. Drishti with a background in behavioural science, myself with a background in mathematics. So we like this kind of topic and talking about stats. And also the Q&A is very much open throughout this whole webinar. So we should have a bit of time at the end for some questions and discussion. So if you have any questions for us or for anyone else, you want to open up the floor to discussion in the chat, then please do put your questions in the Q&A or comments and questions in the chat as we go. Right. So what's this slide about? Well, I thought we might look at some key bits of jargon relating to statistics that are things that we kind of throw around, sometimes maybe not understanding exactly what they mean or 100% understanding how we need to kind of apply them or think about them. And these are some of the words that we came up with when we were kind of brainstorming. We've got 5 here, and we're just going to talk through, I suppose, bust some of the myths maybe around them, talk through what they mean and how we perceive them from our side anyway, to be relevant to a lot of the research that we do and why they're important. So let's kick off with the p-value, something that I think is very frequently discussed within the statistical community as to how relevant and important it is and how we should be using them, and often I think slightly misinterpreted. So I thought I'd go through, I suppose from the mathematical side, what actually is a p-value? What are we saying here? So basically a p-value is the probability of getting your result or something more extreme than that result, assuming that your null hypothesis is true. And if that p-value is small enough, then there's good evidence to suggest that actually your null hypothesis isn't true. So you choose to reject that null hypothesis. So you start with a status quo that you assume to be true, and you see if your data is extreme enough to kind of challenge that status quo. So maybe an example to help us to bring that to life a bit more, a typical kind of example that we might come across with our type of analysis. So suppose you're doing a stats test to determine if mean speeds have changed after you've done a traffic calming measure. So your null hypothesis here would be speeds haven't changed. So there's no difference in the speeds before and after that measure. You then gather some data on speeds before and after. You do your test and you get a p-value of 0.005, which is pretty small. So that's less than 1%. So what that tells you is that there's a less than 1% chance of getting this data under the assumption that your speeds have not changed. And that's the crucial bit. So your status quo is that speeds have not changed, but you've got this data that actually was pretty unlikely, assuming that speeds haven't changed. So that's a small chance. So there's good evidence there that your assumption is wrong, and in fact they have changed. And we often put thresholds on p-values. I think 0.05 is the one that will almost commonly used. 0.1 I've seen used, 0.01 I've seen used, so kind of 1%, 5% and 10%, depending on kind of how sure you want to be. But essentially this is what p-values are measuring. They're measuring the likelihood of you getting this data under your status quo assumption. And we typically take 5% as being, if there's a less than 5% chance, maybe there's something going on here. There's enough evidence to suggest that we can reject our status quo null hypothesis. I'm of the opinion that reporting p-values is a good thing on top of that, and not just saying that it's less than 0.05 and therefore it must be true, because 0.049 and 0.051 are not very different. So I think the context for reporting them is important, and also utilizing other metrics like the effect size to work out how big your effect is. I think it's important to build that holistic picture rather than just saying, oh, it's less than 5%, therefore we accept that it's true. But I'm sure some of you will have different opinions to that. So independence of observations. So simply, each data point needs to be independent from the others. Where might this kind of thing manifest itself in our line of work? Well, suppose you install a new traffic calming measure or a speed camera or something like that, or you're just measuring speeds that people are driving on roads, and maybe there's a new camera that isn't super visible to people. Somebody drives down that road, gets a speeding ticket on day one after the installation, and then tells the whole village through social media or something else that there's a new speed camera at this location. Be careful because I got a big fine. Then of course that's going to influence the driving behaviors of all the other people in that village when they're hitting that location, and you might see that in the data in terms of a sudden reduction in speeds or the like. So it's just being careful that when we are thinking about our data subjects, actually that they are independent from each other. And typically it's an assumption we just brush over. Oh yeah, we've got independent subjects, but there may be some circumstances where actually that's not the case, and it's just worth thinking about that carefully to make sure that's valid. Right, normality. So normal data, I think most of us will know, looks something like that. Looks like your traditional bell curve. And a good example might be the heights of the population of people in the UK. Or maybe we split up into men and women. So heights of men might be a normal bell curve that looks like that with an average of 5'9", 5'10", or whatever the average is. A non-normal distribution has some kind of skew in that bell curve. So you can imagine the bell curve just pushing to the right or the left, and then we would call that skewed data. Why are these things relevant, or where do they come up in our work? So very frequently, these things have to be checked in terms of statistical tests we're doing or statistical models that we're running. So you often want to check that your data fits the normal distribution before doing a stats test, depending on what that test is, particularly if it's a parametric test, not a non-parametric test. Independence is often also important, particularly, well, for any model or stats tests, you typically want to check for some independence. We usually assume collisions are independent, because it's quite difficult to do anything if we assume they're not independent. It opens up lots of technique to us assuming independence. And I think broadly speaking in the analyst community, we see that as a valid assumption. It means we can do collision prediction modeling and statistical testing and Poisson modeling and that kind of thing for counts of collisions. But there are some other things that we have to be a little bit careful of with independence, and casualties is certainly one. So casualties aren't independent in terms of two people in the same car getting injured. There's clearly a dependence between those two people there. The number of casualties in each collision might be something you can assume to be independent. But where we talk about collisions and casualties and other similar metrics, we have to be a bit careful with whether we're assuming those things are independent and why, and definitely stating the assumption if we do. I think that comes up quite frequently. Okay, multicollinearity. So this thing occurs where you've got two variables highly correlated to each other. And for me, at least, this most frequently comes up if I'm trying to build a regression model to understand the impact of a few different variables maybe on collision risk. The problem with this is that it kind of messes up the model a bit, and it can become quite difficult to work out which variable is actually influencing the outcome and to what extent. And it's difficult for the model to pick out the right coefficients for those. So an example I've come across before in my work is speed limit and mean speed. If you try and include both of those things in a model, say as a predictor of collision risk alongside other variables, because typically they're quite correlated, and I'm aware in some cases maybe they're not correlated. If you take rural roads where 60 miles an hour is not very feasible to drive at safely, say, then maybe they're not kind of 100% correlated. But typically speed limit and mean speed are very well correlated variables. And so if you put those in the model together, it's difficult for the model to figure out whether the relation is with speed limit and the outcome, or with mean speed and the outcome, and to what extent. So whenever you're building a regression model, looking at the relationship between your variables and whether they are highly correlated before you put them in is an important kind of intermediate step. Homogeneity, good word, that, a bit tricky to say. So this basically is the principle that your data is drawn from a consistent population. What do I mean by that? Let's go through an example maybe. So suppose you want to understand the relationship between bad weather and speed choice. How does bad weather, be it rainfall, snow, fog, ice, whatever it is, how does that influence people's speed choice? What's that relationship? And in order to do that, you get data from multiple regions across the UK. Perhaps you pick some urban spaces and you pick some rural spaces. You go to Scotland, you go to England, you go Wales, you go Northern Ireland, and get yourself a nice big sample of data, which is obviously a good thing. The challenge with that data is that it's heterogeneous because that's not drawn from a consistent population. And in fact, there might be a different relationship for each region. You might have Scottish people that absolutely love driving in the rain and it doesn't change their speeds at all, versus English people that that's completely different. I don't think that's true, but you've got to account for the fact that you're drawing data from quite different populations there. And so you can imagine having different graphs with different kind of slopes and relationships for the Scots, the English, the Welsh, and the Northern Irish in this scenario. And the analysis that you do, or the model that you build, needs to account for that. And in any data set, you want to be aware of where you've not got homogeneity, where you've got potentially different populations or different variables within that are somewhat hidden that you need to consider. And there are lots of ways of accounting for that. We won't go into those in this webinar, but a mixed model, for example, is one way of accounting for that with random factors and fixed factors. So you could have a random factor in that model, which was region, to account for the fact that you might have different relationships by region, but just something that's important to be aware of with your data set homogeneity. Okay, that's some statistical jargon. Interested if anyone has any other jargon that they'd like to ask about. Potentially that could be a question at the end. Now we're going to move into some principles and pitfalls. So we're going to present to you 5 different simple bits of analysis that we've done and ask you essentially what the pitfall is. What have we done wrong with that piece of analysis? So I'll hand over to Drishti for the first bit.
Yep, I think that it's great to start off with this quote by Daniel Kahneman, who was one of the influential pioneers in the behavioral science space. So he starts off by saying that we can be blind to the obvious, and we can also be blind to our blindness. So the first bit, we're blind to the obvious, is that there can be some clear patterns, some trends in the data that we might not see. But we're also blind to that blindness, that we don't recognize that that's a limitation for us, and which can make it really worse and skew our analysis and maybe give out partial insights. So moving on to the first pitfall. So we've done some bits of analysis and we would appreciate if you could put in your answers in the chat. So the first one being that reported road casualties by road user type, this is DFT 2023 data, it showed that cars are involved in 70,826 casualties compared with 16,978 motorcyclist casualties. Which road user group is at more risk? What do you all think? Give a minute or two for the answers to come in.
If you just stick your answers in the chat.
Yep.
This isn't about being right or wrong. This is just just to get some participation. Okay.
Motorcyclist, okay. We need more information. Do you know who the populations are? Motorcyclists.
I'm wondering if people that are putting motorcyclists have that more information in the back of their minds somewhere.
Okay, so there's consensus that it's motorcyclists and there's not enough information to make that conclusion, and which is definitely right to acknowledge. So if you could click ahead, Nathan. So as you'll rightly guess that we need some of the more context and the exogenous factors. And actually, when we account for exposure, in terms of the per billion miles traveled, that motorcyclists are at significantly higher risk, a 20 times higher risk than car occupants in terms of billion miles travel. So it's really important to account for the context and exogenous factors in our analysis. Yeah.
Yeah, we've obviously picked a bit of an extreme example here where the absolute numbers are very much weighted in favor of cars. And then when you account for traffic, of course, it massively blows up for motorcyclists compared to car occupants. But there are lots of things that are worth considering in terms of these exogenous factors, traffic being a big one, population being another one. I think someone mentioned the number of motorcyclists or cars on the road. So I think it's very easy to read things at face value and miss the context that sits beneath them.
So this is pitfall 2 with some dummy data that we created through Claude. So it doesn't have to represent real world data that we see. So in terms of this data, we're looking at speed camera effectiveness and comparing it with fatalities reduction. So this data portrays that between 1990 to 2000, fatalities reduction was significantly higher than what was seen post 2010. So the study conclusion that was drawn that recent speed cameras are less effective than historical implementations at reducing fatalities. What could be something that's wrong with this analysis?
Answers in the chat, please.
Yep.
Give me a minute to think about it.
Mm-hmm. Compound data. Axis intervals are different.
Oh, you mean on the x-axis? Is that right,
Yeah.
Dan? You mean the x-axis intervals? Yeah. Yeah, good spot actually, yeah.
Yeah.
That wasn't the point we were trying to make, but but very good spot.
Behavior change, an interesting one. The knowledge of cameras goes up.
Yeah, good one. Yeah, good point, Simon. Background level.
Background level of collisions. General downward trend in fatalities over the time period. Yeah.
Yeah, good point coming in.
Yeah. Other factors could have influenced fatalities. Yes. There's more
More
cameras
cameras.
present.
Yeah. Yeah.
Increased vehicle safety. Yeah, that's bang on. You're already a really good analyst. Cars are much more safer. Yes. It doesn't take into account COVID lockdowns. Yes, that's right.
Yeah, that's a good point. Again, that wasn't what we
Yeah.
were getting at, but good point, Paul.
So if you move on to the next slide, Nathan. So as some of you rightly suggested that there's anyway a general downward trend in fatalities. So as we all know that post 2010, we've seen a plateauing trend in fatalities in the UK. So the previous speed cameras, they started from a higher baseline. And we can't just compare post 2010 with just looking and saying that they're not as effective because there's several other factors that we need to consider. Some of you also said that the number of speed cameras have also gone up, as is seen in this other chart. So there's more total length of road covered by average speed cameras. And of course, there's also many other factors such as vehicle safety improvements and other improvements that have led to a reduction in fatalities. So when we do analysis, we need to account for all of these background trends and baselines to ensure that we're making an apples to apples comparison and actually accounting for the exogenous factors.
Great. Okay. Pitfall number 3. So I want you to imagine that I've got this data. So I've put in some kind of intervention, and I've measured the speed changes across 5 sites that have that intervention. So as you can see, we've had a speed decrease in the top 4 of 2, whatever the units are, miles an hour, kilometers an hour. and the bottom one has stayed the same. So I plot a graph, I write my report, and I put this graph in it here. Okay, it's missing axes, and it's maybe not the neatest graph, so that's not the pitfall I'm trying to get at here. Heads up. But I plot my graph, and you can see hopefully that the bar for 2, i.e. speeds after, is lower than the bar for number 1, speeds before. Again, ignore the bad labeling. So my conclusion is that this intervention has worked, and that my the safety, the speed reductions have improved at these sites, and therefore the intervention has worked. What's wrong with that piece of analysis that I've done? There might be multiple things wrong with it, but yeah, what do you think is wrong with that? Sample size, yep, good one first up. Ooh, statistical significant, very nice, Axel, yeah. And there's more statistical significance. Purpose of the intervention, yeah, good point. Yeah, I haven't outlined that, I suppose. Other factors influencing speed, yep. When were the speeds measured? Yeah, true. I didn't give that detail. I mean, quite frankly, it's a poor piece of analysis from me here, really, isn't it? Effect size, yeah, nice. Average of averages, yeah, true. Yeah, that's something to be careful of. Other factors, yeah, comparability, weather, true. There's lots of good things actually that I hadn't even thought of coming through here. Maybe some of you guys want to volunteer to do the next webinar. Great, all right. Yeah, so the thing I was getting at, the pitfall I wanted to highlight was sample size, which I think was the first thing that came out actually. But also statistical significance is important to mention here. So if I do a stats test, I think it was Axel you that mentioned stats testing, then P is 0.07. So I've run a Wilcoxon test. I've run some R code for this exact data. Have a go yourself if you don't trust me that's what the outcome is. But I've got P as 0.07. And typically we wouldn't take that to be a low enough p-value to reject our null hypothesis. And in this case, our null hypothesis is that speeds haven't changed, they're the same. So there's not enough evidence to suggest that speeds have changed. And if we do a stats test, it puts that extra level on of certainty that the sample size isn't really big enough here. If I do this, however, speeds before, speeds after, I've got 10 sites now, and you'll notice I've basically just copied the data and added 10 to it. So we've got 4 decreases in another level. Interested in some guesses here, actually, from some of you. I do another stats test on this data. What do you think the p-value is for a Wilcoxon test on this data now? How different is it to 0.07? Go on, someone be brave. Chuck a number in. No guesses? We got
0.27 and 0.23.
Okay, interesting. So we've got 2 people think it's going to be the same, 0.07 and 0.07. Harish thinks it's going to be 0.03. Any other guesses on what the new p-value is going to be? 0.06. Less than 0.07. Nice, Dan, yeah. Okay, so the new p-value here, so again, I come up with my conclusion, the interventions worked. Notice the same chart. So when I plot this in my report, the chart looks exactly the same as the one above, because the average difference is the same. The p-value has actually gone down a lot. It's 0.006. So I've just doubled the size of the data from 5 to 10, but the p-value is now less than 1% in terms of its statistical significance. Same test, Wilcoxon test, but just having those extra 5 data points has given me a lot more certainty that this intervention has worked. And I wanted to go through this example, I suppose, because I think sample size is a bit of a mysterious concept to a lot of people. You think, oh, well, I'll just use a sample size calculator, chuck in a few parameters, and then it will tell me what sample size I need for this data. But this is kind of what's going on in the background. So you tell the sample size calculator, I want to do a Wilcoxon test. I want to test speeds before versus speeds after, and I'm expecting an average difference of about 2 between them. How much data do I need before I can be certain that that's actually an impact of the intervention, as opposed to just something random that's happening? And here, this is kind of telling you, well, 10 data points is enough with this kind of pattern. 5 data points is not enough at the 5% level. So somewhere in between, you get that tipping point. And that's what the sample size tells you. It will tell you you need, in this case, maybe 7 or 8 data points before you've got a p-value at the 5% level with this pattern of data that you're seeing. And if I continue the pattern further down with similar data of those reductions, then the p-value will get less and less. So that's all that sample size is doing. And now we have that confidence that actually something's happening. Now, I say that slightly lightly because we haven't taken into account other things like potentially a background trend. But it certainly gives us more confidence in this case that this is a genuine effect. Okay, pitfall number 4. So similar setup. We've got 5 sites A, B, C, D, E. And this is the number of collisions I'm seeing the year before at each of these sites. So, suppose I'm a policymaker and I'm looking at this data and I think, okay, sites A and B are dangerous. We need to fix those. So we install an intervention at sites A and B, some kind of traffic calming measure maybe. And then I measure the collisions the year after, and I see this pattern. And importantly, looking at sites A and B, we see 8 at site A, 5 at site B. There's a reduction there in both of those, a pretty decent reduction actually for site B. So my conclusion is that my interventions worked. What's wrong with what I've just done there? What do people think? Yeah, cherry picking, yeah. Bonus points if anyone can get the exact term for the pitfall that I'm getting at. Sites B and E have gone up, yes, yeah. Ah, very nice, Katrina, yeah. Bonus points for you. Yeah, yeah. Yeah, random fluctuations, good point. Exposure, yeah. So the responses are coming in too fast for me to keep up. Yeah, not taking into account the other sites is an interesting one. I've kind of ignored sites C, D, and E in terms of what I've just said, and you'll notice actually that the collisions the year after, it's exactly the same pattern as the collisions the year before, but I just reversed it. So now E and D have 11 and 12 as opposed to A and B. Yeah, lots of you talking about random fluctuations and control groups and things like that. Good stuff. So yeah, there's quite a few things that are wrong with it. So I haven't taken into account randomness of collisions. We know that collisions are inherently random. We can understand them to some extent in terms of the factors that are influencing them, but we can't understand them to its full extent in terms of predicting exactly how many. I haven't looked at background trend. I haven't considered other variables. Also quite small numbers here. If we're comparing 11 to 8 and 12 to 5, is that enough? Maybe we need a stats test. Yeah, nice, Denise. So yeah, what if I gave you some extra info about this and I said, actually, all of these sites, A, B, C, D, and E, they're very similar in geometric design and traffic levels. So they've been picked as a kind of set, and we've looked at them as a set and said which of these are maybe the most dangerous. And also, if you look at the average number of yearly collisions over the long term, then the number of collisions at each site is very similar. It's around about 8 at each site. So with that extra information, what we've done looks quite dodgy. And yeah, what I'm getting at here is regression to the mean. And this is something that comes up very frequently in our work, and just something that we have to be really careful of. And basically, I think one of you said cherry picking at the start. I've cherry picked somewhat. And of course, if you take any given year and you pick the sites with the most collisions, and then you do something to those sites, by the principles of regression to the mean, it's likely that you've seen some extreme values, and then they're going to be less next year, because that's just how these things work mathematically. So whether it was A and B or D and E or whatever that had the highest numbers, they're likely to go down next year. And of course, we might now look at D and E and think, oh, we've got problems at D and E, let's do something there. Oh, and then the numbers go down again. So regression to the mean is of course something we want to be careful of. I just wanted a little nod to the empirical Bayes approach, because this is something that has been used by quite prominent road safety researchers elsewhere. Chap called Elvik, who's, I wouldn't say he's a hero of mine, that's maybe a bit strong, but he's someone that I certainly look up to in terms of road safety analysis, quite a prominent statistician and researcher. This is one of his papers where he uses the empirical Bayes approach to try and combat regression to the mean, which basically combines information about the specific site of interest, i.e. maybe the number of collisions at that site, with a collision model that relates different factors to risk. And that's quite a nice technique that's been proven to work in terms of avoiding those kind of extreme effects. Right, and then finally back to you, Drishti, for number 5.
And moving on to the final pitfall. So we have created some dummy data for comparing ice cream sales in 1,000 liters to motorcycle crashes. So I've just made a simple linear regression, and I made a scatter plot of that. When I did the linear regression for the months of June to September, I understood that the R square is 0.71. So for those of you that don't know, R square measures the goodness of fit. That basically explains the variation in the dependent variable. So in this case, it would be that ice cream sales are explaining 72% of the variation in motorcycle crashes. And I've assumed based on this that there's a causal relationship between these two variables. And as per this current data, I assume that as ice cream sales go up, motorcycle crashes also go up. So my intervention is going to be that stop motorcyclists from eating ice creams, and that's going to lead to lower motorcycle crashes. Now, obviously, that's a silly example, but what do you think is wrong here with this analysis? Yeah, that's right, Dan. It's spurious correlation.
Yeah, good spot, Paul. Yeah.
Yeah, both are caused by another factor. Both increase in the summer. Yes, temperature is the factor that both are influenced by.
Oh yeah, good example, Paul. Ice cream sales and shark attacks. Yeah.
Makes sense, the old writing one, huh?
Yeah, nice, Axel. Yeah.
Nice example. Okay, so if you could click ahead. So as you rightly spotted, correlation versus causation, sometimes we can make some spurious correlations. And while this is just a silly example, and obviously it's really easy to see over here why that could be the case, but in our day-to-day road safety analysis, often we don't realize that we're making these spurious correlations with our data. So if you click ahead. So assuming that police enforcement and more crashes has a causal relationship between each other. If we don't see the chain of causation, we might assume that more police enforcement is causing more crashes, but actually there's bound to be more enforcement where there's more crashes. Similarly, it goes with other interventions such as roundabouts might be deployed where there's more crashes already. So actually looking at the baseline trend, accounting for the longer time trend and understanding the chain of causation is really important when we're doing analysis.
Yep, great. Right, I'm looking at time. So I think we're gonna skip through this section and we'll maybe try and cover it at a future webinar. So there's a bit on stats testing and modeling. Right, because I want to get to a couple of Mentimeter questions to finish, and then if we have any time, we can answer one or two questions after that. So, Drishti, over to you.
Yep. So we would like to understand as a road safety community that what are some barriers that we face for using statistics in our organizations? It'd be great if we can data gaps.
Yeah, that's a pretty big one. Agree with that.
It can be really challenging to get enough data and to deal with those limitations when we're analyzing those things.
Prejudge conclusions, yeah. Yeah, knowledge, resource, training.
Resourcing. Level of confidence. They seem to revolve around three themes, basically, that there's lack of expertise, lack of resources in a way. There's some data gaps that we have to deal with when it comes to real world data, such as a sample size, the quality of the data. And there's obviously the fact that we don't have that expertise as well. And there's data gaps, there's the politics that comes into it.
Yeah, I think that's a nice summary. Yeah, it's a mix of kind of time, capability, resource. Appetite. Budgets, understanding, information.
Agreed scope of work, that's interesting as well.
Yeah, that's an interesting one because I often find that statistics is not super well thought about within a scope. Or maybe it's tagged along, or maybe we could try do some stats with that, but it's not thought about until further down the line. Great. All right, should we move on to the next one?
Yep.
Okay.
So our final Monty question is that how confident do you feel in using statistics for presenting ratios, percentages, or similar numbers, basically the descriptive statistics element of it, or applying a chosen statistical test or modeling data? And hopefully this confidence will increase in the upcoming stats webinars that we have as part of the series.
So basically we're going back to previously what we had in terms of the descriptive stats at the top, stats testing in the middle, and then stats modeling at the bottom. No surprises there, really. Yeah, we didn't put machine learning on this one because we thought it probably wouldn't be relevant for a lot of you. Generally quite a low level of confidence with models, a low to mid level of confidence with testing. I suppose it probably depends on the test, on the context. A lot more confidence on the top one. Good stuff. All right, I think, does that conclude our content?
Yep.
It does. Yes. Okay. So we've got 5 minutes. So we've tried there to give a bit of an intro to this topic, get us thinking about some things, and I think a lot of those bits of jargon, those pitfalls, are certainly relevant to when we do stats testing and modeling. So without going into the specifics of different tests and models, those principles are things we all need to be thinking about that might inform the tests and models that we do and our kind of interpretation and thinking around those. Does anyone have any comments or questions that they would like to leave us with? I'll maybe throw out a question to you, Drishti, if that's okay. We talked quite a lot about quantitative data here, and obviously there are often challenges with quantitative data around sample size, data availability, that kind of thing. I suppose from your background as a behavioral scientist, what about qualitative data? How does that kind of fit into this picture, and how can we be using that effectively?
Yeah, that's an interesting one. So when it comes to the qualitative data, we can obviously focus on some qualitative insights like that we garner from interviews, focus groups, ethnographic studies, so on and so forth. But I think that most researchers, they tend to go towards two extremes, either complete quantitative or complete qualitative, but actually being somewhere in between with mixed research methods and balancing insights from both of them can be really beneficial. So they can obviously, we can't conduct too many interviews or focus groups sometimes because of resourcing, be it in terms of time, expertise, and analyzing qualitative data can be really difficult. But actually balancing the quantitative rigor that comes from the statistical testing side of things and having proxies for things like personality or doing larger regressions wherein you have a dependent variable that can be 1 or 0. So I think balancing both of them can be really helpful.
Very nice. Yeah. I've just seen some of you asking about future webinars. What I'm going to do is just put my email in the chat there. So yeah, if you're not on the mailing list for these webinars, or you've been forwarded it by a colleague or whatever, send me an email. I'll make sure that you are on the mailing list, and that you get sent these webinars. I'd also be really interested in feedback in terms of the right notes to be hitting with this topic, because I'm conscious that for a lot of you, maybe you've done a lot of stats and this felt maybe fairly basic or was a kind of refresher reminder. Maybe for others of you, some of this went over your head a bit or you weren't comfortable with it or whatever. But we want to be pitching things at the right level. We can take things further into the stats world, as I think we want to with this series. But yeah, please do send us either by email, in the chat, whatever. Just send us some feedback on how this was pitched, and importantly, what you'd like to see in future webinars that would support you with your work. What else was I going to say? Oh, and yeah, we'd love contributions as well. So we've got a few potential webinars lined up, but we don't want this just to be me and Drishti talking at you for each of these. If you've done a piece of analysis, whether it's building a collision model, a bit of stats testing, you've done even some machine learning, or something that you think actually has applied some good principles and that people would benefit from hearing about, we'd love to hear from a few of you in this community and get a bit of a discussion going. We've obviously introed and overviewed some of this today, but there's a lot of detail and some case studies, and it would be good to dig into some examples properly. So if you want to contribute to any of these, again, please send me an email, get in touch. I'm hoping we can have a few more of these going through some through some specific examples. Any last comments from you, Drishti?
Yeah, I think that it was a good refresher, but yeah, really looking forward to your comments and feedbacks as to how we can frame these feature sessions.
Good stuff. All right. Is there anything else in the chat that I've missed? Oh, there's a question from Paul. Good question. Right. Well, we'll put that on the list, Paul. We'll put that on the list for next time. Yeah, if any of you have any questions as well that you want covering as part of this, then please do send over some questions, and we can do a bit of a just a question bank session where we go through a few things and discuss some things with you as well. Okay, thanks for your participation. Good to have plenty in the chat, and enjoy the rest of your days. Catch up with you soon.